In this lecture, we are going to see the symmetries in quantum mechanics. Previous class also we have seen about symmetries in quantum mechanics. In that class, we have seen infinitesimal unitary transformation. Today, we are going to see about the finite unitary transformation. As usual, the time translation and spatial translation. This is the unitary transformation series of lecture on unitary transformation part 4. In my previous class, we have seen the infinitesimal time translation. Now we are going to see the finite time translation. Here, instead of a single infinitesimal translation delta t, that is in previous class we have uh, translated the wave function by an amount delta t, where delta t is infinitesimally small one. Here we are going to carry out the infinite decimal time translation for the n time in step tau over n in the limit n tends to infinite. That is, here step size is tau over n and total time is tau. That is, we are repeatedly doing the infinitesimal translation n times. So we will see what will happen. We define the unitary operator u tau, which is a function of Hamiltonian h, which is equal to, when limit tends to n to infinite, uh, that is the product k, product from k 1 to n, 1 plus I over h cross tau n over h tau over n into h, the Hamiltonian. See, we are repeatedly doing the infinitesimal translation by n times. So we are multiplying this. This is the step size, and this is the Hamiltonian operator. So, in the limit n tends to plus infinite, we can rewrite this as 1 plus I over h cross tau, tau into h whole power n, which is equal to e power I over h cross tau h. Here, as usual, h by h cross is a generating function, and tau is the small parameter. So we have seen the unitary time translation operator is u tau, which is a function of h, is equal to e power I over h cross tau h. So when you operate this unitary operator on get psi, that is, if you are operating on e power I over h cross tau h with get psi, it will translate the wave function from psi of t to get psi t minus tau, where get psi of t minus tau is merely the time translation of psi. We will see in detail in my lecture, at the end of my lecture. So you can compare this with the time evolution operator. We know, we have already seen in time evolution operator, the time evolution operator u, which is a function of t naught, is equal to e power minus I over h cross h t minus t naught. So just you can compare this operator with time evolution operator. That is, if you know the wave function at a particular time, you can find the wave function at any other time. Now we will see the finite spatial translations. Here, instead of a single infinitesimal translation epsilon, epsilon is a small parameter in which we are doing infinitesimal translation. Now we are carrying out the infinitesimal translation, time translation for n times. That is, first you do with the epsilon, and again you will do with epsilon. So likewise, you will do it n times. In step up the vector A over n. So the total displacement is A, step size is A over n in the limit n tends to infinite, as we have seen in the case of finite time translation. Now you define the facial unitary operator UA, which is a function of linear momentum, that you have to note here, which is equal to limit n tends to infinite, uh, the product over 1 to n, 1 plus I over h cross. This is the small parameter vector A over n, and the vector linear momentum operator vector P. Uh, as usual, this can be written as, because limit is n tends to infinite. Uh, Within this limit, this product can be rewritten as 1 plus I over h cross uh, a dot p over whole power n, which of course we can write this as e power I h cross a dot p. This is the dot bracket product because it's a vector. Here, p over h cross is a generating function. The unitary operator for partial translation is UA, which is a function of linear momentum, is equal to e power I over h cross A dot p. When this unitary operator act on wave function psi, which is a function of r, that is radial coordinate x, y, z, which is equal to e power I over h cross A dot p psi of r. So we have seen so many times that this is equal to this one is equal to that is e power I h cross I over h cross A dot p psi of r is equal to psi r plus psi, which is a function of r plus a. That is, if the unitary operator ua act on the wave function, it just translate the position in space by a vector a. That is the implication of this expression. Let us transform the operator r into r prime using partial translation operator ua. That is, r prime is equal to ua or ua dagger. So this ua is equal to e power I h cross I over h cross a dot p. Similarly, ua dagger, this plus will become minus, just e power minus I over h cross a dot p. So the now we are changing the uh, operator r into r prime. So r prime is equal to e power I h cross a dot p into r e power minus I h cross I over h cross a dot p. It is well known relation that when a prime is equal to e power I alpha g a into into e power minus I alpha g. This can be expanded. Uh, this relation can be expanded as follows. That is, this is expanded as a plus I alpha commutation of g with a plus I alpha squared by 2 factorial into the commutation of G with the commutation of G with A. So it will go on alpha I alpha q over 3 factorial. It will go up to n. Now you apply this one here, and take, since alpha is a small parameter, you can take the term only the up to the first order in alpha. So this is the up to first order in alpha, that is first two term. You take first two term, that is a I alpha commutation of G with A. If we take that and substitute here, then R prime will become R, this A. Instead of A, we are replacing R, plus I alpha. Instead of alpha, we are using A, that small parameter A, and the generating function is P over H cross. Since H cross is a constant, we are taking out. So this will become I over H cross, and instead of alpha, that small parameter, we are taking A here, and commutation of P with R. So A is the operator, G is the generating function, which is equal to R plus I over H cross A. The commutation of P with R will become minus I H cross. Here you can cancel out the H cross and this H cross. Uh, then you will have only I into minus I. I into minus I is equal to 1. So this will become A. Second term will become A. That is prime will be equal to R plus A. That is what we got when we operate the spatial translation operator with the wave function. The wave function is shifted from psi of R to psi of R plus A. So we have proved this using the commutator relation. So far, we have seen the finite time translation and finite spatial translation. Uh, Now we will see the symmetries and conservation law. Just now we have seen the Hamiltonian of a system transform under unitary transformation e power I alpha g as follow. This just now we have seen for the random operator A prime. So now we are replacing A prime by H prime. H prime is equal to e power I alpha g H into e power minus I alpha g, which is equal to H plus I alpha uh, commutation of g with H plus I alpha squared over 2 factorial, the commutation of g uh, with with the commutation of G with H. It will go on up to I power alpha q over 3 factorial. It will go up to n. But since alpha is a small parameter, we can take up to first order of alpha. That is first two term. We are going to take only the first two term. As I have explained just now. If H commute with G, naturally it will commute with e power I alpha G also, because after all it's an exponential of G. So once it's G commit means exponential e power I alpha G also will commit with H. So, in this case, we may infer two important conclusions. One is the Hamiltonian is invariant under transformation. That is, under transformation, H prime is equal to e power I alpha g H into e power minus I alpha g. We have taken only the first two terms, so this will be equal to H plus I alpha g commutation of g with H, but G and H will commute, and naturally the second term will become 0. This will become 0. So naturally H prime will become H. So that means Hamiltonian is invariant under the unitary transformation. That is one important conclusion. We will see the other one now. If in addition to G commit with H, the operator G does not depend on time explicitly, there is a conservation law that is G is constant of motion. Since we know from the Heisenberg time derivative of expectation value of operator, we have seen it. That is a time derivative of expectation value of G is equal to 1 over I H cross expectation value of the commutation of G with H. If G is explicitly depends on X, sorry, t time, then one extra term will come. This is that is 1 over I H cross expectation value of commutation of G with H plus expectation value of expectation value of delta G over delta T. So we assumed that G does not depend explicitly on time. Then the second term will become zero. This will become zero. So naturally, we have seen already this also will become zero. Computation of zero. So the time derivative of expectation value of G will become zero. That means uh, this G is a constant. Only if you differentiate a constant, then you will get zero. So that is G is constant in motion because of this Heisenberg relation. So whenever the Hamiltonian is invariant under unitary transformation, the generator of the transformation is conserved. Here the generator is G. In general, that for every invariant symmetry of the Hamiltonian, that correspond to conservation law. That is a second important conclusion. Now we will see the conservation of energy and linear momentum. Uh, First, we will see the time translations are generated in the case of time independent Hamiltonian by evolution operator. You know the time evolution operator U, which is a function of t naught, is equal to e power minus I over h cross into h into t minus t naught. Since you know very well, H commute with generator of time translation. Here, generator is H over H cross, which is given by H itself in this case. So it is invariant under time translation. Just now we have seen it. As H is invariant under time translation, the energy of the isolated system is conserved. That is one important point. Now we will see about the spatial translations. The linear momentum is invariant under the uh, unitary operator and the unitary operator UA, which is a function of P. That is spatial unitary operator, and the position operator transform as follows. We have seen this when a unitary operator act on p prime, it will p will unitary operator act on unitary operator act on p, then P will become P prime. So P prime is equal to P. Similarly, we have seen the position operator act on R, then R prime will become R plus A. Just now we have seen. This is just a partial transformation. That is, we are adding a small factor A. Since the Hamiltonian of a free particle does not depend on coordinate, because the potential energy depends on the coordinate XYZ coordinate, not the kinetic energy. So total Hamiltonian is p squared over 2m plus v, which is a function of x. Since for a free particle v is equal to 0, this h commit with p, because h contain only p squared over 2m. P will commute with P. So this will become 0. That means the Hamiltonian is invariant under spatial translation. That is, H prime is equal to U H U dagger. Here U is e power I over H cross A dot P. H e power I over minus I over H cross A dot P. Here you know very well that P and X commute. So you can change the order of the operator. So you take the H to the right hand side, then the multiplication of this U dagger become 1. So naturally this will become H. So H prime will become H prime will become H. That is, the Hamiltonian is invariant under the spatial translation. Since H and P commute and the linear momentum operator does not depend explicitly on time, then P is a constant of motion, because the according to Heisenberg relation, that is, the time derivative of the expectation value of an operator is equal to 1 over I h cross the expectation value of commutation of that particular operator with the Hamiltonian h, plus the expectation value of partial derivative of that operator with respect to time. So here we are taken P as an operator, so this will become 1 over I h cross P commutation of P with the h. Uh, and there is no time dependence explicitly, then this will become 0, because there is no explicit time dependent. And also P and H commute, this also will become 0. That means time derivative of expectation value of P is equal to 0. That means P is constant. So if H and P commute, the Hamiltonian will be invariant under spatial translation, and linear momentum, that is P, will be conserved. This is another important point. The invariance of the system under spatial translation means there is a symmetry of spatial homogeneity. The requirement for homogeneity of space implies that spatially displayed wave function, that is psi, which is a function of r plus a small vector a, much like psi of r, which satisfies the Schrodinger equation. That is, symmetry of time homogeneity gives rise to the conservation of energy, whereas symmetry of phase homogeneity gives rise to conservation of linear momentum. These 2 points are very important. Thank you very much for watching my videos and supporting me continuously. My YouTube channel ID is youtube.com/c/vasu v physics. Thank you very much.